In the name of Allah, who is most merciful and beneficial. Today I am going to represent midterm presentation of organic chemistry. First of all, let me introduce myself. My name is Kiran Aslam. I am from BS Chemistry and my ID is 005. Topic was assigned to me is cycloalkane. First of all, I want to tell you presentation layout. In this topic, I will tell you definition of cycloalkane, types, then we will see its preparation, in which we will discuss different methods. Then we will discuss its physical properties, its addition reactions. Then we will see conformational analysis of cycloalkanes and then strain energy. What are cycloalkanes? Cycloalkanes are the compounds that contain only carbon-hydrogen bonds and carbon-carbon single bonds. This is similar to alkanes, but in cycloalkanes, the carbon atoms are joined up in a ring. Cycloalkanes are also known as naphthenes, but they are distinct from naphthalene. The smallest cycloalkane is cyclopropane, in which three carbon atoms joined with each other in a ring form. Cycloalkanes have sp3 hybridization, means every carbon make only sigma bonds. As we can see in propane, each carbon is attached with two hydrogen atoms and with other two carbon atoms through sigma bond. So it is sp3 hybridized. They are represented by general formula CnH2n. Cycloalkanes are aliphatic in nature, means they don't have alternation of double and single bond. They are also known as alicyclic compounds. If alicyclic compounds contain only carbon atom in the ring, then they will be regarded as carbocyclic compounds. But if there is at least one other atom rather than carbon, then they will be regarded as heterocyclic compounds. This is a series of cycloalkanes: cyclopropane, cyclobutane, cyclopentane, cyclohexane, heptane, and so on. These are their molecular formula, the boiling points, melting points, and densities. The boiling point increases when the number of carbon atoms increases, and the melting point also decreases. For example, cyclopropane has melting point minus 128, cyclobutane has minus 91, and the liquid densities increases when the number of carbon atom increases. These are the structural formula. Here three corners, it means that it has three carbon atoms. Each corner contains one carbon atom. In cyclobutane, there are four corners, it means it contains four carbon atoms. Similarly in pentane and hexane. Know the preparation of cycloalkanes. We can prepare cycloalkane by the dehalogenation of dihalides, which is regarded as Freund reaction. In Freund reaction, we treat 1,3-dihalopropane with sodium in the presence of ether. It will convert into cyclopropane. Then the next is modified Wurtz reaction. In this reaction, 1,5-dibromopentane is diluted in the presence of zinc. It will give cyclopentane. Hydrogenation of cyclic alkenes. When we do hydrogenation of alkenes, it will convert into cyclohexane. In the presence of palladium and ethyl alcohol, and conditions are 25 degrees Celsius temperature and 1 atm pressure. Diels-Alder reaction. It is cycloaddition reaction which takes place when a conjugated diene, this is diene, reacted with a compound containing a double bond called dienophile. Both will react and give a product, cycloalkane. Then the Simmons-Smith reaction. This method was developed by Simmons and Smith, so it is named as Simmons-Smith reaction. In this reaction, first the methylene group is transferred by organozinc compound. Diiodomethane react with zinc copper to form a carbonate carbene-like compound. Then this carbene-like compound will react with alkene. Here transition state forms. Then this transition form convert into cycloalkane with the removal of zinc iodide from cyclic ketone. Whenever the calcium or barium salt of a dicarboxylic acid is distilled, a cyclic ketone is formed. For example, barium adipate, it will give cyclopentanone, and when we do the Clemmensen reduction of the cyclopentanone, it will convert into cyclopentane. Know the physical and chemical properties of cycloalkanes. The properties of cycloalkane are similar to alkene, but due to the presence of ring, it has some difference from the properties of alkanes. For example, cycloalkanes are more tightly packed and solubility because of their low polarity like alkanes. Cycloalkanes are almost insoluble in water, but they are soluble in solvents which have low polarity like benzene, ether, and tetrachloride, etc. Density. Cycloalkanes have less density. It have densities less than 1 gram per ml. And I have already told you that the density increases when the number of carbon atom increases. Stability. We can evaluate stability of cycloalkane by the heat of combustion. But what is heat of combustion? The amount of heat which is evolved when 1 mole of a compound is burned completely to carbon dioxide and water is known as heat of combustion. Higher the heat of combustion, it means the compound is less stable and vice versa. Heat of combustion of cycloalkane is greater than alkanes, hence they are less stable than alkanes. The higher heat of combustion of cycloalkane is because of ring strain. Ring strain is maximum in cyclopropane and it decreases when the number of carbon atom increases. Means cyclopropane has more ring strain, but when we move toward the cyclohexane, cyclohexane is more stable because it doesn't have ring strain. What is ring strain? Ring strain in a given molecule is because of the contribution of three factors. First is angle strain, second is torsional strain, and the third is non-bonding interactions. We will discuss each of them one by one. First, we will see what is angle strain. This strain arises because of the deviation from the bond angles. We know the bond angle of the cycloalkane is 109.5, but if a compound have less or greater angle than 109.5, it will create angle strain and it become unstable. For example, in cycloalkane, each carbon is sp3 hybridized. So the angle between orbitals should be 109.5. But in case of cyclopropane, as we can see from here that the angle in cyclopropane is 60 degrees. So it is less than 109.5. It will cause angle strain and it will become unstable. And if we talk about cyclobutane, the bond angle between cyclobutane is 90 degrees. So it has angle strain of 19.5 degree. It is less than cyclopropane because it has one more carbon than cyclopropane. Torsional strain. Torsional strain occurs because of the eclipsed hydrogens. Or we can say any deviation from the staggered position. Staggered position is the most stable position of any compound. So any deviation from the staggered position will cause strain in the molecule, and this type of strain is regarded as torsional strain. If the dihedral angle decreases, then the torsional strain increases. But if the dihedral angle is an angle between the plane of the two bonds, dihedral angle is maximum in staggered arrangement. As I told you that the staggered form is stable for any compound because in staggered form the dihedral angle is maximum. So the staggered form of cycloalkanes will be more stable. The third is non-bonded interactions. Any two atoms in a molecule that are not directly bonded may interact in several ways, depending on their size, polarity, distance between them. These interactions may be attractive or repulsive, resulting in increase or decrease in the strain of the molecule. If distance between atoms is less than the sum of their van der Waals radii, the molecule is said to be under strain called steric strain. If the molecules if the atoms present in a cycloalkane repel or attract, then it will cause instability, and this is due to non-bonded interactions. Know the reactions of cycloalkanes. Cycloalkanes can undergo addition reaction, substitution reaction, combustion, and aromatization. We will discuss one by one. First, addition reactions. Catalytic hydrogenation. When we do the hydrogenation of cycloalkanes, by providing temperature up to 80 degrees Celsius in the presence of catalyst, its ring will be break and it will convert into propane. The next is addition of halogens. When we add halogen in cycloalkane or cyclopropane, it will convert into 1,3-dibromopropane by the opening of ring. Then the addition of hydrogen halide. When we add hydrogen halide, it will form N-propyl bromide to ring opening. Substitution reactions of cycloalkanes. Halogenation. When we do its halogenation, the hydrogen will replace with chlorine atom. The hydrogen atom will replace with chlorine atom through a free radical mechanism. Then the next is combustion. On combustion, the cycloalkanes are converted into carbon dioxide and water with the evolution of heat. Aromatization. Cyclohexane or its derivatives may be converted into aromatic compound by catalytic reforming. This is aromatic compound which have alternation of double and single bond. So when we do aromatization of cycloalkanes, it can be converted into aromatic compounds. In this reaction, hydrogens will be removed, and here the double bond will form with the elimination of hydrogens. The last reaction is isomerization. Cycloalkane may undergo isomerization in a similar way as the alkenes. Isomerization may lead to open chain compound or change in ring size. For example, here the ring will be opened, the cyclopropane will be converted into alkene, and here the carbon change in ring size. It contains 6 carbon, but it contains 5 carbon atoms. Know the conformational analysis of cycloalkanes. As we know, in cycloalkane, the carbon atoms are sp3 hybridized, which would imply an ideal tetrahedral bond angle of 109 degree wherever possible. But in actual, it doesn't happen because of ring strain. First of all, I want to tell you what is strain energy. The strain energy of a cycloalkane is the theoretical increase in energy caused by the compound's geometry, and it is calculated by comparing the experimental standard enthalpy change of combustion of the cycloalkane with the value calculated using average bond energy. As I have already told you about ring strain, which is caused because of angle strain, torsional strain, and non-bonding interactions. Now we will discuss ring strain of cycloalkanes. So first, ring strain of cyclobutane. The ring strain of cyclobutane is slightly less at around 110 kJ per mole. But a cyclopentane has a ring strain of about 25 kJ per mole. Its ring strain is less than cyclobutane because the carbon number because cyclopentane has one more carbon atom than the cyclobutane. And if we talk about the cyclohexane, there is no ring strain. It is stable compound. Now I will tell you about the stability of cyclohexane. First, I want to tell you conformational analysis of cycloalkanes. We can see here the angle is 60 degree in cyclopropane. So it causes angle strain and it become unstable. And this is cyclobutane. Its angle strain is less, but it is still more stable, more unstable because of the eclipsed hydrogen. Means it has torsional strain, which make it unstable. Cyclopentane. Cyclopentane has very less angle strain, but it has effective torsional strain because it has 10 eclipsed hydrogens, which make it unstable. No cyclohexane. We will see why it is stable. As we can see here, if we draw this structure of cyclohexane, it will have angle strain because its angle is greater than the internal bond angle is greater than 109.5 degree. But it converts into this form. This is its staggered form. Here all hydrogens are aligned and it doesn't have any type of strain. So it is most stable. This is the chair conformation of cyclohexane. Cyclohexane can make chair conformation and board conformation, but the chair conformation is more stable because it doesn't have any type of strain. The angle is 109.5 and all hydrogens are staggered. This is the chair conformation of cyclohexane and this is the board conformation of cyclohexane. This is more stable, but it is unstable because it has non-bonding interactions. There are two type of hydrogens, axial hydrogens and equatorial hydrogens. The hydrogens in blue are axial and the hydrogens in gray are equatorial. In cyclohexane, 3 carbon atoms pucker up. As we can see here, the black carbon are puckered up and the 3 carbon atoms pucker down around the ring. Each carbon in cyclohexane has two different kind of hydrogens. One is axial and one is equatorial. Axial bonds are oriented above and below, but equatorial bonds are oriented around the equator. An important conformational change in cyclohexane involves ring flipping. Ring flipping is a two-step process. First, it converts into board form, then it undergo a flipping. In flipping, the axial hydrogens convert into equatorial and equatorial convert into axial. And an up carbon become a down carbon. The chair form of cyclohexane are 7 kilocalorie per mole time more stable than the board forms. The board conformation is destabilized by torsional strain because the hydrogen on the 4 carbon atoms in the plane are eclipsed. Additionally, there is steric strain because two hydrogens at either end of the board, the flat pole hydrogens, are forced close to each other. So the board conformation is unstable. Note that the equatorial position has more room than the axial position. So when we attach substituent, it is more stable on the equatorial position than the axial position. For example, here we can see in 1,3 diaxial interaction. If the substituent is attached on the equatorial position, it is 95% more stable. But if it is attached on the axial position, it is 5% stable only. Di-substituted cycloalkanes. Cycloalkanes may form cis isomers and may be trans isomers. Cis isomers, we will say if the two substituents will be attached on the same side. This wedge bond means the bond which is coming forward on the plane, and the dotted bond means the bond backward. Here both bonds are on the same side, so it is cis isomer. But here the both bonds are on opposite sides, so it is trans isomers. They are stereoisomers of each other. Stereoisomers are isomers that differ only in the way the atoms are oriented in space. The prefixes cis and trans are used to distinguish these isomers. A disubstituted cyclohexane such as 1,4-dimethyl cyclohexane also has cis and trans isomerisms. In addition, each of these stereoisomers have two possible chair conformations. First is trans 1,4-dimethyl cyclohexane and the second is cis 1,4-dimethyl cyclohexane. This is trans because the bulky groups are on the opposite side, and here the bulky groups are on the same side. So it is cis and it is trans. So that's all from my side. Thank you.